I'm showing in the center, I'm using this transformer, but unlike the Faraday and Tesla, which use the sine wave voltage to drive it and the resultant sine wave current in the primary and secondary, I'm now driving this voltage with the square wave voltage and looking at the two quantities. Integral of square wave voltage, according to Faraday's law, becomes a current, a flux in a flux in a core. But if I measure a current in the primary and with smaller, current sense winding or so on, I can have observe the current in the driving the core, and I can observe the flux in the core. Now, my standard question is, when I want to challenge you, they both look linear, right? But if I start increasing the magnitude of the drive, and remember, the drive is now 50%, positive voltage, negative voltage with a zero, so it's a volt-second balance, flux balance. So, but if I increase the drive, then what happens? Oh, you see, one is a linear and the other one is showing the spikes. Which one you think is a flux and which one is the current? Well, you see, the Faraday's law simply says the flux is integral volt seconds. If I drive it with square wave voltage, integral of a square wave is a triangular. No if, buts, and maybes. But because the core has its nonlinear characteristic, the more I drive the core toward the edge of the saturation, the more it will have a smaller slope and it will have a current. So this spiky effort here shows that the actual current will be distorted and the flux is never distorted, right? And it really reflects that at this point, I'm going into the magnetic characteristics of the core, which is no longer in a linear region of magnetic material, it's starting going to saturation. And the more I drive it, the more I get there. And you see the two big points I make. When you have a square wave voltage drive, you have automatic volt seconds. That is exactly the same what happened with the 60 hertz transformer. What's happening with the 60 hertz transformer? Positive sine wave drives the core in a positive direction, and the negative sine wave resets the core back to the origin. So it can periodically and the power transfer happens during both positive and negative cycle. And that is not happening with most of these other transformers, which are now claimed to be called transformers, but they don't do that. Example, forward converter, flyback stores all the energy and things like that. Anyway, the point, and this is square wave voltage drive, so that means you have to make a switching converter such that its transformer, if it is square wave, and especially if it is not square wave rectangular drive, that it has a flux balance. And also you have to make sure that it has a charge balance, which is automatic in a transformer 60 hertz, but in a switching converter, no. That's why let me just finish this demonstration and see what it's going to show.
Input voltage source is a net zero average,
no.
And we can change it by increasing the drive.
Yes, can you hear the sound? It's beauty. It's beauty. You hear it and I don't hear it. So it's blame it on Zoom, okay? I don't know why I don't hear it, but
we can also change. We can change the duty cycle of the switch.
Hello.
And these are basically the main parameters that we'll be changing in the experiment. Now let us look at the picture of the DH loop on another scope.
Yeah. Now
and if you look at it on a horizontal, we have amperage and excitation. On a vertical, we have a...
Can you hear me? Yes? Okay, what I'm doing now, I have two scopes. On one scope, I'm looking at a voltage drive, and I'm looking at the resulting current and resulting flux in the core. Now, when I put a flux as a function of current, I'm using the other scope in the so-called XY coordinates, and of course, what will that show? It will show the really BH characteristic of the magnetic material, and you see that high slope. And if I drive it,
and if you look at it on a horizontal, we have amperture excitation. On a vertical, we have a.
Okay, so that is one demonstration, and the other is transformer saturation. Let's see here. Can you see that?
Loop.
Yeah.
Let us now examine in closer details what are the parameters responsible for the saturation in the switching converters and in the magnetic devices in general. First, if we excite a core with a square wave voltage with identical positive volt seconds and negative volt seconds, we will excite the core flux linkages in one direction, shown in red, and de-excite it with the same amount, and therefore, in a steady state, we will have the periodic excitation up and down along this linear part of the curve. If we are still in a linear part of the curve, we will have corresponding current to be of the same linear shape. Let us now look at what is the main equation. As we see here, the volts per turn that the single device, magnetic device, can support.
Okay, this is a very famous saturation equation. Now you can see when I was inferring to the fact that we go from 50 hertz of Tesla and Faraday at the time, and we go now to 50 kilohertz, that is how much higher frequency. It's 1,000 times higher frequency. Agree?
Yep.
1,000 times from 50 hertz to 50 kilohertz. Switching frequency is now easily done at 50 kilohertz. They're doing useless 500 kilohertz and 5 megahertz, but even at 50 kilohertz, which is above the audio range, so you wouldn't hear it, if you have a frequency from 50 kilohertz, increase 1,000 times, what can you do with the cross-section? Because the product, flux saturation, flux density times the frequency is something that you have to make volts per turn less than this number. So 1 volt per turn, say 5 volts and 5 turns, it's 1 volt per turn, has to be less than this. That means that you see here that saturation flux density is a constant, say for ferrite is 0.5 Tesla, so it's fixed. But the product of cross-section of the core and product of the frequency at which you're driving is what determines this 1 volt per turn. So if I increase the frequency from 50 kilohertz to 50 hertz to 50 kilohertz, what is how much I reduce size, cross-section? 1,000 times. Is that right? And yep. And if we have, remember this core at 50 kilohertz, that's nothing. Most of ferrite cores can be driven full flux from 0 to 300 millitesla in one direction and 0 to minus 300 millitesla in the other direction without getting huge core losses. So core losses will be still negligible. But the size will be reduced 1,000 times. Did we manage to do that? Absolutely not. We are far away from it. Far away. And you know what? In the meantime, we did go from, in fact, when I started back in, and I had a couple of my classmates who were doing a PhD at the same time, who are working in the industry and so on, we were all excited. Say, oh, all we need to do is go from now 50 hertz, go to 20 kilohertz, and everything will be small size and beautiful. Didn't happen. Didn't happen by factor of 100. And not only that, the whole field that I warned back in 1988, 30 years ago, the whole field went bananas, you know, and going to make devices which can switch in megahertz and now 10 megahertz and now talking about 100 megahertz and so on. Did they get anything smaller in size? Absolutely not. All they did is increase the losses and nothing else. They have nothing to show for it. And why? Because the whole field of power electronics. I'm sorry, that's why I made this cartoon. It went in the wrong direction. It went in direction that not following to make a true you have to make magnetics in switching converters, which will follow the rules that were set up, except we cannot do what Faraday or Tesla did, that automatically when he had a sine wave driven voltage source, you have positive and negative flux, which are automatically volt second balanced or flux balanced. So there is no problem of driving the core in the saturation, as long as the magnitude of that is proportional to the, for a given frequency, proportional to the core size. You have to have a core size proportional to that frequency. As you see here, the higher frequency, you can get smaller core size, okay? That's one thing. And the other thing, which is automatic with the secondary side, conducting the current, which when reflected the primary is subtracted from, and adding to that is fixed magnetizing current, you have an input current, which is just slightly bigger than output current, reflected output current. And that's the circulating current. Now, you know what the theory is that everybody in power electronics was talking, Dr. Chuk, why are you insisting so much, you know, that it's a AC transformer type? I don't care. Transformer is a two-winding on a magnetic core. Yes, provided you know what you're doing and provided you put all the thing around it, switches, capacitors, and inductors and transformer in a configuration which will provide flux balance and charge balance. And that's what all the converters in a classical technology don't do that. And I'll show you in a minute why. And I'll show you my initial step. I did 45 years ago, my invention of my Chuk converter, which was the first time really applying properly the principles that you needed to do to make a transformer work, okay, in the right way. And since that time, I hopefully have some chance to introduce you to some new structures which break new ground. And in fact, my current work is dramatically changing in the sense that after so many years, I figured out how to get, you know, proper way of transformer such that we can truly get 50 or 100 times reduction in the size of magnetic core, and still at 100 kilohertz, which is the only operating frequency we could use. Then likewise, there are other applications. So the main thing is we need to change system, not devices. And the whole power electronics field was driven in the wrong direction for the last 50 years, driven in making new devices and trying to justify their use by using the outdated, obsolete technology of system, which should have long time not even ever used it, but it ended up being used anyway. So the other area that I'm focusing on, and I hopefully show you today, is the area of everybody now needs microprocessors and need to drive them at 1 volt and 100 amp or 800 amps current. Again, this whole area system-wise is totally, going sideways, because instead of making one converter which does that, and it's small and doesn't have a magnetics, it has automatic, drive. They are now using 12 of these. Not only one buck converter, which I proved that is useless, but they use 12 buck converters in parallel. And now the latest invention that was made by some of the companies, not to mention, is to replace these inductors with the 12 transformers. You know, so this have boondoggle, and of course requires a capacitor which are 100 times more than necessary. So, and you know, how do you? The problem is that the present field of power electronics, people who are in it, they think that's ICT design. The more devices you use, the more capacitors and more inductances, the better it is. Absolutely not. Power conversion is just opposite. You need to do as much as you can with as little devices that you can use very efficiently. Anyway, so this is a point that I show this.
It has to be less than this quantity given here, which is directly proportional to reducing the core. So the silicon by a factor of 2 or 4 to the core, or just showing here by reducing the voltage drive, we can essentially reduce the flux excitation in the core and avoid the saturation, just like by increasing again and get out of the nonlinear region.
So you see what I showed, by increasing the frequency, you're reducing the, you're reducing the ripple, reducing the current and reducing the flux. So that's the point. Higher the frequency, smaller the flux proportional to it. But, you know, we now go from 50 kilohertz to 50 hertz to 50 kilohertz, 1,000 times increase, and we get a 2 times smaller size. We're doing something wrong, okay? Clearly. All right, let's stop there, and let me move to the other subject, which is really key.